All right. So just to give you a forewarning, this video is going to be a little lengthy, and I'm going to split it up into a few different parts because of the program I'm using. I want to make sure that it does record, but I do want to tell you that the lesson we're about to learn is the foundation of the rest of first semester calculus. It's a very important video, and so I know it's rather lengthy. I know it sucks that it falls on an e-learning day. It is what it is. But if you find yourself kind of daydreaming, I would pause the video and then make sure you come back to it, and really when you're paying attention, take notes and stick with it. So what that guy was just talking about is the foundation of calculus, and that is, how do you find instantaneous rate of change? How do you find out how fast something is going at one instant moment in time? Because we know how to find out, if you travel 90 miles and it takes 30 minutes, we can find the rate that way, but we never really talk about at an exact moment. And so that's what we're going to talk about today. And I've mentioned this on the first day of calculus, that all of first semester calculus it's all about slope. And so we're going to start this lesson with how to find the slope of a line. And we know slope of a line to be rate of change. So I can't tilt this so you guys can see. Slope is just rate of change. So that's nothing groundbreaking. And the way you find rate of change, you find the change in the y over change in x. Because you guys know the slope formula to be y2 minus y1 over x2 minus x1. You're finding change in y over change in x. If you've had a physics class, you know the symbol delta. Change is denoted by delta. So change in y, we call delta y. Change in x, we call delta x. And so we've kind of dealt with a couple problems in this class already that have had delta x in it, but that's what it means. It means how much does the x change. So look at this first one. It says how to find the slope of a secant line. A secant line is when you take 2 points on a graph and you connect them and it hits the graph twice, and all you want to do is find the slope of that line. This is just the generic slope formula. If you know 2 points on a line, you could find the slope of that line. Take y2 minus y1, 5 minus 2, over 3 minus 2, 3 over 1 is 3. So again, that's what we've been working on since you guys have been in 6th grade, 5th grade, whenever. But what we want to do is find the slope of a tangent line. You know how to find the slope of a line given 2 points, but how do you find the slope of a tangent line, meaning at 1 point? So for instance, if I wanted to find the slope of the tangent line at P, and when I say slope of the tangent line, here's the tangent line at P, how do you find the slope of a line if you only know 1 point on it? And that's the whole big first question of calculus. How do you find the slope at one particular point? Well, the first thing we're going to do to talk about this is rename these points generically. Up here, I gave them numeric values. I want to name them generically. And here's what I mean by that. So I have C right here, and this function is f of x. Well, I want to talk about how can we write point P using this notation C. C stands for an x value, which means point P would be the ordered pair C comma, so C is the x value. The y value that we associate is, well, think about if you find a y value. If you evaluate a function at C, you plug C in for x, and so f of C would be the corresponding y value at C. So point P, instead of giving it numbers, we're just going to call it C comma f of C. Q gets a little more interesting. So from P to Q, we shift over a certain amount of x right here, right? To go from P to Q, we have to go to the right a little bit. We have to change our x value. Well, that's where delta x comes from. From C to Q, we're changing some sort of x amount, right? From point P to point Q, we're shifting over some sort of x amount, which means if we're going to name Q, think of what the new x value would be. From the origin, we're going over C, and we're going delta x more. So the x value would be C plus delta x. That's the x coordinate, whatever the C value is plus delta x. Well, just like we plugged in the x value here to get the y value, same thing. If we plug in C plus delta x to the function, we get the y value. So f of C plus delta x. So we renamed these points. We have C comma f of C and C plus delta x comma f of C plus delta x. And think about if we wanted to find the slope of that secant line between Q and P using this notation. Let's just use our normal slope formula. If I want to find the slope, we would take y minus y, so f of c plus delta x minus f of c. This is just us finding the difference in the y's, subtracting the two y coordinates, over, well, now let's subtract the x's, c plus delta x minus c. So you notice the c's cancel, and you have f of c plus delta x minus f of c over delta x. This is the generic slope formula. This means the same thing that you've learned back in 5th grade. You have y2 minus y1 over x2 minus x1. So delta x is just change in x. That's what we talked about right up here. That's your change in the x values. That's what delta x stands for. On top, you're subtracting the y values. This is known as the difference quotient. E-N-T. This is known as the difference quotient. It's basically the slope formula, just using different notation. Okay, so what we want to do is find the slope, but we want to take Q and move it really, really close to P. Think about what we're trying to find. We're trying to find the slope of the tangent line at P. So let's take Q and move it as close as we can to point P, because think about this. If we move Q really close to P, like let's say I put Q right here, and we draw that secant line, notice how the slope of that line is getting pretty close to the slope of the line we want. Well, think about if we move Q even closer to P and draw it. Now we're getting really close to an approximation for the slope of that tangent line. So what we're going to try to do is move Q as close to P as possible. All right, so think about that. And then think about what happens to delta x as we move Q really close to P. Okay, get this visual here. Think of Q getting really close to P, and think of this delta x. Think of what's going to happen here. This delta x is going to shrink, 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 shrink as Q gets really close to P. Or in other words, we're trying to get delta x as close to 0 as possible. This is why limits come into play. We're trying to get delta x to approach 0. We want to get delta x as close to 0 as possible. So what we say is, as Q gets closer to P, delta x becomes smaller. Right? We just talked about that. As we move Q closer to P, delta x becomes smaller. Okay. We get to a more accurate value for the slope of the tangent line. So as we move Q really close to P, and as delta x gets really, really small, we're getting really close to what that slope of the tangent line is. So here's what we use limits for. If we want to find the slope of the tangent line at point C, f of c. So for our problem here, that's what point P is, C, f of c. If we want to find the slope of the tangent line at point C, f of c, here's what we do. We take the limit as delta x approaches 0. We're trying to get delta x as small as possible. We're trying to get it down to 0 of that difference quotient we just talked about. This right here is going to be pretty important for us moving forward in the next few problems. This finds us the slope of the tangent line at point C, f of c. We want delta x to approach 0, and then we just want to calculate this slope. So notice right away we would plug 0 in for delta x, and we're going to have some issues occur. Well, let's see what happens when we use this. This is similar to what happened in the velocity problem we've just done, where it says t is 4 seconds, and you plug it into that limit, and you do some work, and you get that denominator to cancel out. We're going to try to get this delta x to cancel out. All right, so let's see what happens. Example 1. Find the slope of the tangent line to the graph of f of x equals 3 minus 2x at negative 1, 5. So we want the slope of the tangent line to this function at negative 1, 5. So what we're going to do is apply this. This finds us the slope of a tangent line at a particular point. Okay, so we take the limit as delta x approaches 0 of f of c plus, I'm just going to rewrite this right here. I want to get used to writing this. C plus delta x minus f of c over delta x. Now, those of you that are in physics with calculus, you have already learned about derivatives. For your assignment tonight, and I think possibly for next assignment, you're not allowed to use those shortcuts. You maybe can use them to check and see if you have the right answer, but I want you to use this process because physics uses all the derivative rules. Calculus gets into why do they exist? Why is what you are doing in physics working? And so we're going to use these limit definitions to do our problems. And you can be mad, but you'll deal with it. So understand what C stands for. C stands for an x-coordinate. It stands for the x-coordinate of the point that we want. So notice here it says at negative 1, 5. Negative 1 is our C value. That means wherever we see a C, we replace negative 1 instead. So we're going to take the limit as delta x approaches 0. F of negative 1 plus delta x minus f of negative 1 over delta x. So notice wherever I saw a C, I put negative 1 instead. Okay, well, we still have an issue. We can't plug 0 in still. So now what we need to do is figure out what f of negative 1 plus delta x is. We need to do our evaluations for the function. We have to plug these inputs into the function, and let's see what happens. So remember, the thing inside the parentheses, negative 1 plus delta x, that's your input. That's what we are going to plug in for x. So we're going to have the limit as delta x approaches 0 of 3 minus 2 times negative 1 plus delta x. So this, I'm plugging negative 1 plus delta x in for x. That's what this is. So this thing right here is f of negative 1 plus delta x. Minus, so we're going to bring this minus sign over, whatever f of negative 1 is. So now we have to figure out what f of negative 1 is. So input negative 1 to the function. And you get 3 plus 2, so you get 5 over delta x. We still have some cleaning up to do. We have to distribute the negative 2, and remember, ultimately, we're trying to get this delta x to disappear. So we have the limit as delta x approaches 0 of 3. We're going to distribute the negative 2. So we get positive 2 minus 2 delta x minus 5 over delta x. We can combine like terms in the numerator. 3 plus 2 is 5, and minus this 5, that cancels. So the limit as delta x approaches 0, 5 minus 5, it goes away. So you have negative 2 delta x over delta x. And now we're getting somewhere because the delta x's cancel. Now you can apply the limit. We're going to plug 0 in for any delta x we see, which is none, and what we have is just negative 2. Remember, if you have the limit of a constant, it just equals the constant. Negative 2. So understand what this is. I think it's so important that as you go through a problem, number one, think about what you're doing as you go through a problem. But number two, when you get to an answer, think about what you just found. I think that's underrated. So many times throughout this course I found last year, people would be like, I know how to do it, I got the answer, and then they would never think about what they found. We just found the slope of the tangent line to this graph at this point. And try to think about this. Think about what this would become if you graphed it. If you graph this, you get a line that has a slope of negative 2. So really, for any point, I could have picked any single point on this line that I wanted. The slope's going to be negative 2 because this is always going to be negative 2. That's not always going to be the case, but I just wanted to make a connection there. All right, so moving on. Find the slope of the tangent line to g of x equals x squared minus 4 at 1 comma negative 3. Okay, so we want the slope of the tangent line to this function. That means we're going to use that limit definition. We're going to take the limit as delta x approaches 0, g of, remember we're going to place the c with the x coordinate, so that's our c right now. So we're going to have 1 plus delta x minus g of 1 over delta x. So wherever we see that c, we put a 1 instead. Now we need to do our evaluation. We want to figure out what g of 1 plus delta x is. So input 1 plus delta x into the function. So the limit, as delta x approaches 0, we're going to plug 1 plus delta x in for x. So 1 plus delta x squared minus 4. That's what g of 1 plus delta x is. Minus g of 1. So now let's plug 1 in. So we get 1 squared minus 4. That's negative 3. So minus negative 3. And that becomes plus 3 over delta x. So now we have to do our cleaning up. We have to do our manipulation, use our algebra. We have to square this binomial. So we have the limit as delta x approaches 0. Let's square the binomial. You have two options. You can either put it twice and FOIL it out, or use a little shortcut. I use it every time. You square the first term, you take the product and double it. So delta x and double it, so plus 2 delta x, and square the delta x. That's how you square a binomial. Square the first, double the product, square the second. Negative 4 plus 3, that's just negative 1 over delta x. The 1's cancel, so that's nice. And then notice in the numerator, each term has a delta x in it. And we've already done problems like this early in the semester, just 5 classes ago, but this is why, to practice for this skill. We're going to factor delta x out of the numerator. Because remember what we're trying to do? We're trying to cancel this delta x out down here. So we have the limit as delta x approaches 0. We're going to factor delta x out of the numerator. And so you have 2 plus delta x over delta x. Now they cancel. So you've eliminated the problem. And now you can substitute 0 in for delta x. And so you get 2 plus 0, which is 2. So what we just found is the slope of the tangent line to this function at 1, negative 3. And I want to show that graphically. You don't have to draw this if you don't want, but I think it's important to understand graphically what we're doing as well. So I'm going to graph this function, x squared minus 4. It's going to be a parabola. The y-intercept's negative 4. The x-intercepts are going to be 2 and negative 2, if you would solve it out. So real rough sketch. Draw the parabola. And look at what happened. Let's plot 1, negative 3. So at 1, negative 3, it's on the parabola right here. What we're claiming is that if we draw the tangent line to that function at that point, we're saying the slope of the function, or the slope of the tangent line at that point is 2. That's really what we found right there. You're picking a point on the function, on the graph, drawing the tangent line, and we're finding the slope of it. And this is there's so many applications that we're going to get into when we do this. Right now, you're just saying, so what? That's a random line on a curve, so what? But we're going to get into all the applications of what this does. Okay. I'm going to go ahead and pause this right now and create another video. So at this time, if you're starting to daydream a little bit, take a break, stretch, whatever, and then come back and watch part 2.